All right, part two of the video on electron configuration. Again, before we looked at just regular raw electron configuration, we had the following setup where we started with 1s2, and then we did the second energy level 2s2, 2p6, 3s2, 3p5. So that's a regular electron configuration for chlorine. Well, what I want to do and what you need to do is something called orbital notation. And for your notes, orbital notation involves the arrows. And what we're going to do is instead of drawing electrons as numbers, we're going to draw electrons as arrows. And we're going to draw those electrons sitting in orbitals. So if we review here, we remember that there's an s electron that has one orbital, and it's going to look like this. Here's the s sublevel has one orbital, and it's going to look like this. There's the one orbital. P has three orbitals, so it's going to look like this. D has five orbitals, so it's going to look like this. And F, which we'll rarely use, is going to look like this. 1, 2, 3, 4, 5, 6, 7 orbitals. Okay? So that fulfills the 2 electrons max, 6 electrons maximum, 10 electrons maximum, and 14 electrons maximum, because each orbital can hold 2 electrons. Okay? All right, so if we take let me erase this stuff. Let's do the orbital notation for chlorine. And the way we do that is we start off the exact same way. But we start off with 1s. We draw an orbital. Now I want to draw these 2 electrons as competing or oppositely spinning electrons. So we draw an arrow going up and an arrow going down. And then we do 2s. We do the same thing. P, as we just drew, has 3 orbitals. Electrons going up and down. We have 3s, and now we have 3p. 1, 2, 3. Now, according to the Pauli exclusion principle, you can't have every orbital gets 1 electron, and then you double up. So you start off with 1, 2, 3, 4, 5. So you start out, so that's how it works. Now, what if you only have to have 1 electron? Well, you only put 1, but you have to draw the other 2. In other words, if you have a d electron, 1, 2, 3, 4, 5, and you only have to have 4 electrons, then you leave the last one blank. Okay? But you notice the pattern of filling here. Actually, let's do oxygen. Let me erase this. If we do oxygen, it looks like this. 1s2, 2s2p4. This is the electron configuration. The orbital notation would look like this. 2s2p, 1, 2, 3. Watch. I have to draw 4 electrons. 1, 2, 3, and then you double up to 4. Okay? Let's try another one. Let's do titanium. Let's do a nice big one here. Titanium is 1s2. I have to draw 22 electrons. 1s2, 2s2, p6, 3s2, p6, 4s2, and then 3d, 1, 2, 3, 4, 5. Don't forget to draw all 5, but I only need, let's see here, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I only need 2 electrons. So that's the correct orbital notation for titanium. Okay? So it follows the exact same patterns that we had before. We just have to include the Pauli exclusion principle, or the Aufbau principle. Anyway, that's that. Now, next thing we have to take a look at is some special points of stability. Now, we know that we're going to use chromium and copper's typical configuration. However, it is incorrect. So what I want to do is touch on this for a second. So chromium is 1s2, 2s2p6, 3s2p6, 4s2, 3d4. Now, if you take a look at the last 2 sublevels, I had this one, 4s is completely full, and d is really nothing special, but it's almost half full. So what I'm going to do is going to take an electron from the 4s2, and I'm going to take that electron and move it up here to make 3d5. So 4s1, 3d5. I now have a half full and a half full combination. So as we see, the special points of stability, half full, is one that is a special point of stability. That's good. So chromium is one you will have to worry about, for at least me. If you're watching this video just for review, just know that chromium is one of those elements that has a special point of stability. Copper's similar, although not exactly the same. You end up with 1s2, 2s2p6, 3s2p6, p6, 4s2, 3d9. You'll notice again, this is full and this is almost full. So what it does is it takes one of these electrons, moves it up here to make 3d10. So now I have half full and full. This is another special point of stability. So if I have full, half full, or in this case half full, full of the last two orbitals, I have something that is extremely, or that is a little bit more stable than what we typically had. So copper and chromium are the ones you need to worry about, at least for just regular high school general chemistry. Other than that, we won't worry about it any further. Now, the full combination, let me talk about this. These are our noble gases. So when we have our noble gases, anything right here, this has a full S and a full P. So this is very, very stable, very stable. This is a full S, this is a full P, this is very stable. This has a full S, a full D, and a full P, again, very stable. Okay, so I have 3 points. So anytime I have a full combination of sublevels, then I have something that is extremely stable. Okay. All right, the last thing you need to worry about is something called the highest actually, the second to last thing is something called the highest occupied energy level. And the highest occupied energy level is basically, of the energy levels listed in the configuration, you have to talk about the highest one. Now, this is the third, and believe it or not, this is on the third period. The highest occupied energy level for nickel is 4. This is on the fourth period. The highest occupied energy level for iodine is 5. It appears in 2 places. It's on the 5th period. So the highest occupied energy level shows us what period these things are on. Okay? And one last thing we need to talk about, and let's go back to this slide, and that's going to be noble gas configuration. So noble gas configuration is a shortcut. We'll call this the shortcut. Now, what if you have to do, we just saw iodine real quick. What do you have to do the configuration for iodine? This would stink if you had to do this every time. 1s2, 2s2, p6, 3s2, p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. That would stink to have to draw that every single time. So what we can do is a shortcut. And we start the shortcut off the same way. Okay, iodine, except now we're going to put a set of brackets. And the shortcut is we're going to use the noble gases configuration. So what we're going to do is we're going to go to iodine, which appears on the 5th period. We are going to use the noble gas on the 4th period, and that would be krypton. So we're going to put Kr in here. Now, for iodine, I have to get 53 electrons. I'm just making little notes down here. Krypton now has 36 electrons. So by putting krypton in brackets, I have now represented 36 electrons. Well, that is this many electrons right here, 36. So I don't have to draw these because I just drew them right here. So what do you do now? Well, you know that iodine starts on period 5. And the first sublevel is always S, and you keep going. 5s2. So now 36 plus 2 electrons is 38. And then you have 4d10, and that's 48 electrons. Again, I'm just making notes down here. You don't have to write this stuff. And then I have to have 5p5, and that is going to be 48 plus 5 is 53, which is exactly what I need. So this is the noble gas configuration. It's just a shortcut. Okay. All right. Any questions on this? Let's see me. I know I didn't do a ton of examples on this. Just trying to keep these a little bit more concise. Okay. That's all I got.